Welcome back to the channel, Adventures Through Climate Change, with me, Trevor. Yep, I host this show. I'm the only one that does it. It's just for fun. I'm just trying to get a community together. We take an armchair approach to climate change, watching other people's videos, trying to diagnose what the heck is going on. What should we believe about climate change? What is it? I mean, should we just be tossing more money? Like, what is the true effect of carbon dioxide? What's the if we were to do nothing, what would be happening with the normal cycle of the climate on Earth? These are all questions that we are trying to answer, and we've been watching videos for like almost the last 4 months, 3, 4, 5 videos a week, hopefully. And sometimes some weeks, are bad weeks. I work. This is just for fun, just to get a community together, because I got tired of talking about this type of stuff, and with people that don't care and that don't know. So I was like, you know what? I'm going to inform myself even more. I'm going to watch other people's videos. So that's what we're doing here. Today, on today's video, the plan to fertilize the ocean with iron. Atlas Pro. Okay. We're subscribed. We're liked. Let's get it up here. Let's get going. It's like a 15-minute video. Let's do this.
Floating in just a single drop of ocean water are thousands, possibly millions, of microscopic organisms called plankton. In Greek, planktos means wanderer, which is a pretty good description of these organisms, since all they do is float near the surface of the water, completely dependent on the currents to move them along. These can further be divided into phytoplankton and zooplankton. Phyto also comes from ancient Greek and means plant, while zoo comes from the ancient Greek zoon, meaning animal, and these feed on the phytoplankton, similar to how animals feed on plants at our scale. Together, these two types of plankton form a huge and diverse ecosystem completely invisible to the human eye. And yet, it was these creatures that have had by far the largest impact on life on Earth. Seriously, it was around 3 billion years ago, when the Earth was only about 1.5 billion years old, that cyanobacteria, Earth's most abundant phytoplankton, produced the first gaseous oxygen as part of a chemical reaction we'd later call photosynthesis. Now, with this highly reactive gas present in the atmosphere, new types of chemical processes and therefore organisms could develop. Except these ones respired using this toxic byproduct of the plants to fuel the creation of their own organic matter. This is known as respiration. Between these two types of organisms, photosynthesizers and respirators,
Beautiful.
an interconnected community, or in English, the first true ecosystem, developed. Essentially, it was these cyanobacteria, these phytoplankton, that jump-started all other life on Earth. But as life became more complicated and widespread, it began to have new effects
It's
on
my
the
type of
planet.
place.
Occasionally, these plankton would die and fall to the bottom of the ocean floor, out of the reach of organisms that could consume them and recycle their organic matter. In short, decomposers could not decompose them. Eventually, this dead organism would be buried by other sediments coming from above, and all the carbon it took from the atmosphere would become trapped beneath the ocean floor. This process is called the biological pump, as it takes carbon from the surface and sequesters or pumps it into the subsurface. And because Earth is more or less a closed system, this has had some gradual but global scale consequences. Over millions to billions of years, atmospheric carbon, mostly in the form of carbon dioxide or methane, was drained from the atmosphere and stored into sedimentary rocks. This constant drain of carbon from the Earth's atmosphere eventually depleted it, and what started out as an atmosphere of roughly 30% carbon dioxide, 10% methane, and 60% nitrogen became one with only 0.04% carbon dioxide, 0.0002% methane, 78% nitrogen, and 21% oxygen. Oh yeah, and almost 1% argon, but that's not really important. Because CO2 and methane absorb and retain more energy from the sun's rays than either oxygen or nitrogen, this change caused the Earth's atmosphere as a whole to absorb and retain less of the sun's energy. Less energy means less heat, and over millions of years, the Earth changed from an extremely hot and humid place into the one we know now, where ice can exist year-round at the poles and deserts are the prevailing land biome across the planet. But in recent years, this trend has actually begun to reverse a little. Another organism, this one much larger, called humans, maybe you've heard of them, have begun to undo the effects of the biological pump. You see, some of the organic matter that was stored beneath sediments over time became what's known as fossil fuels, an easily available energy source that can be used to power all sorts of really cool things. As a result of humans using these fossil fuels, carbon that was once sequestered underground has now been returned into the atmosphere. The effects of this trend reversal is a reversal of the previous climate trends, for where the Earth was becoming colder and more desert, this increase in atmospheric carbon works to make the planet warmer and more humid, like it once was millions of years ago. This isn't really a problem for the planet or even life, as they've both survived much worse, like meteors and volcanoes worse. The only thing that this really poses a problem for is those humans, as they are the ones that have developed to depend on the Earth being the way it had been, so that their crops can grow and their cities remain out of the dangerous reaches of natural disasters. Recognizing this, some humans have tried to come up with a solution to their problem. All sorts of ingenious and creative methods have been laid out to fix this problem of fossil fuel consumption, such as not doing this as much, or promising to hardly do this at all in the future but doing just as much now. But those methods have turned out to not be quite as effective as we had hoped, so scientists have also looked at ways to just undo this issue, to reverse their reversal of the biological pump, or in English, a way to put carbon back into the ground so it stops changing the weather. Although massive in terms of scale, the biological pump is rather slow when compared to how fast humans can recover and expel fossilized carbon. But if the rate at which carbon is put back into the subsurface were to be increased to equal or greater than how much we as a society can produce, then climate change would essentially be resolved. Of course, that's a lot harder than it sounds. Or is it? No, it is, but we're still going to look at ways to do it anyway. A couple weeks ago, I showed you this map in my Oceans Are Deserts video, which shows the abundance of chlorophyll A in the ocean. This is necessary for photosynthesis to take place, and therefore shows how much primary productivity is occurring here. Green into red is where there's a high level of production, dark blue to purple is very low levels of production. What we can see is that the majority of the ocean is consumed by these large cells of low productivity, with higher productivity only really straddling coastlines and polar waters. This is actually why tropical waters are usually so clear, as there's hardly any organisms or organic matter in them to block light from passing through, while colder waters have much greater amounts of those microscopic plankton that absorb the light for energy, making the water more opaque. And not to spoil my other video where I talk about this, but essentially this distribution of productivity is the result of nutrient distribution across the surface of the ocean. Where there's more nutrients present, there will be more productivity. Where there's less, yeah, okay, you get it, there'd be less productivity. After learning this, researchers, as well as many of my viewers, suggested that if we simply add nutrients like nitrogen and phosphorus to these vast areas of deficient ocean, we could create huge blooms of phytoplankton which could draw in large amounts of carbon, effectively combating the changing composition of the atmosphere, reducing climate change. Now, ignoring any effects these blooms might have on other marine ecosystems, maybe watch my video on eutrophication to understand that a little better, this plan still has some flaws. Perhaps the biggest of which is that the production of chemical fertilizers relies on what's known as the Haber-Bosch process. In order to produce ammonia, an input of nitrogen from the atmosphere is required, as well as hydrogen extracted from natural gas, which is already not good, plus the input of energy, which is also derived from fossil fuels. In the end, this process consumes a ton of fossil fuels, and the use of these fertilizers afterwards would never be able to recoup the atmospheric carbon they produced when created. But there's still one last idea that researchers have come up with. But to understand it, first we need to go back and talk more about ocean nutrients. Because when studying phytoplankton populations and different nutrient abundances in the Southern Ocean and the equatorial Pacific, researchers made an interesting discovery. In these parts of the ocean, neither nitrogen or phosphorus or any other macronutrient was deprived in the water enough to limit growth. And yet, primary productivity was still low. The next question to ask then is, if it's not these nutrients limiting growth, what is? Looking deeper into this, the researchers found that there actually was one element in the water that was unusually depleted: iron.
Sasha,
Oh,
all interns must complete the Duncan run. There it is.
we almost made that. I was getting into it. Are we 6 minutes in yet? 7 minutes, 8 minutes. We got another one. We got 4 ads too. I don't pay for that. Awesome. YouTube. I don't, guys. I'm sorry. I'm a cheapskate. Ask my wife.
Somehow, iron was greatly influencing ocean productivity in certain areas of the ocean. Further research only supported this idea, such as the Vostok ice cores taken in Antarctica. By drilling into the small air bubbles trapped in this ice core, we can see what the atmosphere of the Earth was like when they first formed, going as far back as 420,000 years. And when comparing airborne iron levels against global climate records, it was discovered that for each period of global cooling, iron dust concentrations were greater in the air and particle sizes were significantly larger. The opposite was also true, and warmer times in Earth's history saw a reduction in atmospheric iron concentrations. And we can assume that if there was more iron in the atmosphere, then there was more in the oceans as well. So basically, a higher iron abundance in the ocean appears to be linked to lower global temperatures, and that link is thought to be through an increase in ocean productivity. Putting everything we've learned together, these create a feedback loop, where low global temperatures cause less water to evaporate from the ocean, making the planet overall less humid. Less humidity results in more of the Earth becoming desertified. More exposed desert means more sands are blown into the air by the wind, leading to an increase in iron deposition in the ocean. This increased abundance of iron causes higher productivity in the oceans, and with more productivity, the biological pump sequesters carbon at a faster rate. Less carbon in the form of CO2 and methane causes further lowering of global temperatures and
Okay. Low global temperatures causes lower humidity. That makes sense, right? I mean, you see humidity when it's super hot because, that's what, I'm not going to get into what liquid to gas phase. But anyways, increased desertification. So lower humidity, increased desertification. Lower temperatures, increased desertification because it kills everything off. Because, wouldn't higher temperatures called desertification? Oh, my dog is barking. I'm sure you guys can hear it. It's terrible. Increase iron concentrations. I can see that. So increase iron concentrations because when you have more deserts, the wind blows more, and then it blows the wind. We talked about that with breaking down the albedo when it becomes more tundra-like and the wind picks up and less plant life to block it and less everything, higher concentrations of CO2 or lower concentrations of CO2, right? And so it blows the dust around. Higher ocean productivity, yes, that's because the increased iron, more minerals, and the higher rate of biological pump from the higher ocean productivity. That makes sense. And then that goes back to low global temperatures because you got a higher rate of biological pump. Let's do this.
In the ocean. This increased abundance of iron causes higher productivity in the oceans, and with more productivity, the biological pump sequesters carbon at a faster rate. Less carbon in the form of CO2 and methane causes further lowering of global temperatures and
less
allows
CO2.
this cycle to continue. Okay, I know that was a lot, but we're not quite done yet. So now we know the role iron plays in...
Okay, and that makes sense because we found with Mr. Ralph Ellis that, and you guys should watch those videos. Those were really interesting. That increased desertification is directly correlated with low CO2 levels, right? Yeah, plant life likes CO2, right? Okay, I think so.
And affecting global climate, but we still don't really know why iron influences productivity in the first place. If iron isn't considered a vital nutrient for phytoplankton, or really any plant for that matter, why does it appear to be impacting them in such a huge way?
The rusting.
Well, as it turns out, iron is what you'd call a micronutrient and can play an important role in the very specific functions of different organisms. In humans, for example, we need iron for a protein called hemoglobin that makes up a substantial part of our blood. Functionally, it's the iron in the hemoglobin that oxygen attaches to in our lungs, where it's then transported to our cells, allowing us to continue on with cellular respiration and, be alive. As it turns out, iron plays an analogous role in many phytoplankton like cyanobacteria, in enzymes like nitrogenase. Except instead of picking up oxygen, the iron found in nitrogenase enables the enzyme to pick up, well, yeah, you guessed it, nitrogen. And as we all should know by now, nitrogen is the top nutrient required by essentially all life on Earth. So it's iron that controls the ability of many phytoplankton to absorb other nutrients, and that explains why iron was found depleted in some of these ocean waters while no other nutrient was. They couldn't pick up any other nutrients because there wasn't enough iron. I'd also like to point out again where these iron deficiencies were found. In the Southern Ocean and the Equatorial Pacific. This makes perfect sense because if you remember a second ago, I said the only real source of iron in the ocean comes from dusts being blown off from land. So yeah, the middle of the Pacific Ocean, also known as the furthest place from any major landmass on the planet, is exactly where there'd likely be the fewest inputs from land. As for the Southern Ocean, while it does surround Antarctica, it receives very little iron from the land here, as basically all of the continent is covered in ice, therefore trapping any iron that could escape and fall into the ocean. And it was here that all of this was put to the test in experiments like the Southern Ocean Iron Release Experiment, or SOIRE for short. In this experiment, scientists took powdered iron and dissolved it into diluted sulfuric acid. Once properly prepared, this iron mixture was released in an area over 50 square kilometers in the open ocean south of New Zealand. Initially, about 3,800 kilograms of this solution was introduced into the water, but on day 3, 5, and 7, additions of between 1,550 kilograms and 1,750 kilograms were added as well. Now, because most phytoplankton can reproduce within a week's time, the results were observable almost immediately. The research crew stayed on location for just 13 days and found the phytoplankton abundance and therefore the primary productivity to have increased by as much as tenfold in the test area. Once the team left the site, they continued monitoring it using the SeaWift satellite and observed that the resulting phytoplankton bloom created by this experiment remained distinguishable for over 40 days after they left, or over 50 days in total. Since then, several other similar experiments of varying scales have been conducted in the Southern Ocean, each time with similar results. Basically, yeah, adding even trace amounts of iron can drastically increase ocean productivity in certain areas. And this has led a lot of people to wonder if we could potentially use iron instead of other chemical fertilizers to stimulate oceanic productivity, thereby increasing the input of the biological pump, potentially sequestering some of the carbon we've released back into the atmosphere through the burning of fossil fuels. But this is, how should I say this, also not a great idea for many different reasons. First off, mathematical predictions suggest that even if stimulated with iron to the point where phytoplankton in the Southern Ocean incorporated 100% of the free nutrients in the water over the next 100 years, at most 15% of the carbon released from fossil fuel combustion could be drawn in from the atmosphere and transformed into organic matter. So this already couldn't be the only thing we did. However, just because it has been turned into organic matter doesn't mean this carbon has really been sequestered. And most of this carbon would eventually return to the atmosphere through decomposition, either fairly soon after the initial bloom, or over the next few hundred years if it became mixed with deeper ocean currents. Typically, the biological pump can only sequester about 0.05% of the carbon taken into the ocean by primary production. So, only about 0.75% of our total emissions would be sequestered, which means we would have to do this for hundreds, possibly thousands of years before its effects became pronounced. Add on to this the fact that extracting and processing iron still requires a large amount of fossil fuel input, starting with mining it, then transporting it, and ending with the refining process. Even if we only used recycled iron, we'd only be reversing damage done at a less efficient rate than we created it, and again would leave a net negative. In short, I do not believe this is a viable method to help tackle climate change, but by studying systems and relationships like these, we can gain a better understanding of how the Earth works, and therefore create better models, better predictions, and potentially better solutions to the problems we face. If you agree with me on this, then maybe you'd also agree that it's important to have people who share and explain these ideas to the general public at no expense to them, so that they can gain public support and possibly even become a reality. Unfortunately, sometimes those people need a reliable source of income to support themselves from, let's say, a site like Patreon. If you'd like to help support me, like all these generous people, and get more videos like this one,
if you feel like he deserves it, join his Patreon and whatnot. I'm not going to go through that whole thing because it's already a longer video. Atlas Pro, fantastic. The plan to fertilize the ocean with iron. That was from 4 years ago. Let's break it down. We saw that video the other day that, was from 10 months ago, and it did say, it was the one that piqued my interest about the iron. It did say that it was beneficial and actually could do quite a bit. I don't know. More research, less research. maybe not less. More research needs to be done, possibly. Is it a rabbit hole we're chasing? Possibly. I don't know. We're going to have to find this stuff out. And we'll just watch more videos, I guess, because sometimes I feel like we're going in circles with stuff. But then you get those things in the video that affirm other things that you've talked about in other videos. And you're like, okay, so there's some legitimacy here. It's a different perspective, right? So do I think it could help? I do think that maybe we should consider something like this. It wouldn't be that hard to dust the ocean as a Freightliner's going home, already carrying stuff. Hey, let's just dump some dirt from time to time, right? Hey, you're required to carry dirt and dump it. I don't know. I don't know if that's what we should be doing, but it seemed like it could be a possibility that there might be minerals in that dirt that aren't in the ocean, or that other plant life or animal life or prokaryotes or whatever can't get to because they stay at the surface of the water. Not positive. Interesting stuff. I think we're going to have to watch more. I hope you enjoyed the video. Maybe I earned your subscription. Maybe he earned your subscription. Maybe you give somebody a like, me, him, doesn't matter. I do hope to catch you on the next video and lay down a comment if you want me to comment back, reply. Okay. We'll catch you on the next video.